My name is Manjunath Bhatt, and today I'll be presenting my final project for financial computing. My project is a visualization tool that compares several path planning algorithms like Dijkstra, A star, RRT, RRT Connect, RRT star, and PRM in obstacle filled environments. In robotics, it is very important to compute safe paths very quickly, but deterministic search algorithms like Dijkstra and A star can become very slow in high dimensions or cluttered spaces. So, random sampling algorithms like the RRT algorithms often generate feasible paths far more efficiently. So, let's try to visualize how this works. I'll run the random sampling algorithms first since they're quicker. And let's start with the RRT planner. So RRT explores the whole search space by randomly sampling points and constructing a graph. And once it reaches the goal, we have a final path, as you can see this green line here. Next, let's look at RRT Connect. It grows two trees from the one from the source and one from the goal. And as soon as those two trees connect, we have a path. As you can see, RRT Connect ran slightly more quicker than RRT because you have two trees growing together, which helps faster convergence. But both these paths aren't necessarily the absolute shortest path, and every time we run the algorithm, we get a different path, but it is quick to generate these paths. Now let's look at RRT star, which combines the ideas of Dijkstra as well as RRT to obtain a very smooth and short path, almost close to the shortest path. And as you can see, this tries to go in between the obstacles and minimizes the distance traveled by the robot. So RRT star is an optimal variant of RRT, and this is its search space. Now let's look at A star. A star is a deterministic algorithm which will always give you the absolute shortest path, and it is a grid-based algorithm. Here it's trying to, it has a heuristic that tells, that gives an idea of where the destination is, and it also tries to minimize that heuristic as well as minimizing the distance from the source, like in Dijkstra. And as you can see, this is the absolute shortest path that you can have in this configuration. Next, we'll move to PRM. In probabilistic roadmaps, PRM stands for probabilistic roadmaps. We generate a graph by randomly sampling the points and then we run A star on this graph. You can run A star, you can run BFS or Dijkstra. For this implementation, I've chosen A star. So here it first creates a graph and then runs A star, and you can see it has created a fairly good path here. The randomness comes from the graph that you start with because PRM randomly samples nodes and obtains like the k nearest neighbors to get the neighboring nodes. And finally, let's look at how slow Dijkstra is. So Dijkstra is the traditional classic algorithm that we have learned in class, and it explores every node symmetrically in all directions. It has no idea of where the goal is and explores each of its neighbors. It's going to take a long while to converge to the final path, and hence it is pretty difficult to use in the field of robotics or whenever you need quick replanning, or if you want to find paths multiple times in a given environment, or if your goal keeps changing, you can't run Dijkstra, you would want quicker paths like RRT or RRT star, which RRT star gives you a good balance between the optimal shortest path as well as the computational time. Exploring the search space very slowly, and eventually it will find the absolute shortest path once these blue visited nodes reach the destination. The path returned by Dijkstra and A star are identical and will be the absolute shortest path. Thank you.